Chemical bonding, and in this chapter the topics that we are going to take a look at, as you can see, is obviously Kossel-Lewis approach to chemical bonding. Yes, that's where we will start with, and then we will go to octet rule, covalent bond, Lewis representation of simple molecules, formal charge, limitation of the octet rule, ionic or electrovalent bond, lattice enthalpy, the bond parameters. So till here it is not very important for JEE, right? But then again, we cannot let it go off because these are the basics of this chapter. So if you don't learn this, we will not be able to understand a lot of other chapters in inorganic chemistry, like P block, the coordination compound, S block, DNA block, and we cannot afford to do that because inorganic chemistry holds 30% of our JEE paper. We cannot do that, right? So we will have to read about this, and then from VSEPR theory, VBT, hybridization, MOT, bonding in some homonuclear diatomic molecules, and hydrogen bonding. These are the main important parts for your JEE Mains and JEE Advanced. So let's take a look at it without much further ado. Okay. Now the story of chemistry, right? Where does it start from? It starts from atoms, obviously, correct? And about that we have learned it in structure of atom, and we know that how atom look like, right? How does an atom look like? Basically, if I have to draw it, this will be an atom. Inside this, right here, will be our nucleus where we have the protons and the neutrons, and these will be the shells where our electrons are roaming around, correct? Yeah, this is basically what we learned, correct? Now we also got to know, my dear students, that the atoms, right? The atoms, they don't like staying alone, just like us. Of course, some of us, like me, I don't like being with anyone. I really like staying alone. I think I enjoy my company the most. In short, I'm a loner. Anyway, but there are people, we like having someone around. We like having friends. We like having our families together, isn't it? We do like that. And very similarly, the atoms were also found to exist together as one species, and they have the characteristic property. And such a group of atoms, we started calling it molecule, right? Great. Okay, molecule, we understood that atoms they stick together. We call it molecule. Amazing. Now, you know when a molecule exists, let's talk about the family. So, you know, when you have a friend, right? You connect with your friend. There's a bond, right? It could be because you share notes. That could be a bond. Or it could be an emotional one, right? But in a family also, you have a family bond. You have an emotional bond between you all, which holds the family together, or which holds that friendship bond together, isn't it? Very similarly, when these atoms, they stick together, they form a molecule. Do you know what holds the molecules together? Nothing else but a chemical bond. Yes. So how do we define a chemical bond? The definition would be the attractive force. There is an attraction, right? Even in your family, you have an attraction with your mother or your father or your sibling. That is why you are staying together. There is an attractive force. Of course, you fight sometime, but even then, it is an attractive force that bonds you all together. And very similarly, the attractive force which holds various constituents, atoms, ions together, right, in different chemical species is called a chemical bond. Now let's take a look at it. This is, my dear student, let's say, this is the the molecule of H2O. Right, this is the molecule of H2O. So these white ones are your hydrogen, the red one, this is your oxygen. Okay, and let's take a look at the chemical bond. As you can see, look at how these two hydrogen bonds, they're coming together. They're sharing one electron each, and they are forming a covalent bond. Now, what is a covalent bond? We will read about it in some time. Okay, all right. So this is easy peasy biryani tasty, right? No doubts here. I hope. Even if you have, you write it in the comment section. I'll definitely answer. Okay. Now moving on, Kossel-Lewis approach to chemical bonding. What did these guys say? Why is it so important? So Kossel and Lewis, their approach to chemical bonding actually came up during Bohr. Yes. So when Bohr had given his atomic theory, they took some inspiration from there, and that's when they came up with their approach to chemical bonding. So now Kossel says that let's not make our life too tough, and he says that, so you understand how the atom is, right? He said something like this. Take a look at it. He said that imagine that this is the nucleus. This is the nucleus. This blue pen is your protons. Let's say protons and neutrons are inside, and these are the electrons that are revolving. And here is the outermost shell. This white part is the outermost shell where your electrons are roaming. So let's consider this part, the nucleus and the inner electrons, to be something called as kernel. What did he say? He said that let's call them something as kernel, K-E-R-N-E-L, as you can see right here. Okay, he started calling them kernel. Great. And he said that, see, any which way in a chemical reaction, who takes part? It's always the valence electron, the last shell electrons, they take part. Unless it's a transition element, when the inner electrons and the outermost electrons, they're almost of same energy, and that's when they want to take part. But most of the cases, it is the outermost electrons, they take part. So why complicate life? Why do we have to even study about the inner electrons? Let's only study the outer electrons. Let's call it to be kernel. Great. Now Lewis said that, let me make it even more easier for you. Okay, let me make it even more easier for you. Do I have a cube here? I see that I do have a cube, but it's a huge cube that I will not. Okay, I found a laptop here. Okay, I found a laptop here. So let's consider this to be Lewis. So Kossel said that, let's call it kernel. Now Lewis said that, imagine this atom to be a cube. Cube, you know what is a cube, right? Cube has what? It's like a rectangle but in 3D. So he said that at the central position you have the kernel. And he said that all the corners, like you have 1 and 2 corners here, then 3 and 4 corners here, 5, 6 corners, 7, 8. All the 8 corners are where you have the 8 electrons. Okay, that's exactly what he made. See, at the center right here you have the kernel, and these are the electrons that are holding this position. Okay. Now further he said that, he postulated that atoms, they achieve the stable octet when they are linked by chemical bonds. Okay. Yes. So he said that it's the octet when they are absolutely stable, and they love it. All right. That's what he said. Great. Makes sense, right? Makes sense, everybody? Amazing. Okay. All right. Now what happens? So it's because of the octet. Let me just explain it a little bit. So you know that the noble gases in periodic table, right? That helium, neon, argon, xenon, radon, krypton, and all of that, they have 8 electrons in the outermost shell, right? And because they have 8 electrons in the outermost shell, they're very stable. They don't want to mingle with someone. They're like, you're peasants. I don't want to meet with you. Yeah, go away. No mingling, right? They do that. So now Lewis and Kossel said that basically what happened was all the other elements, they only want to attain that octet. They only want to attain that 8 electrons in the last shell so that they can be stable. That's what he said. And because they want to attain that stability, they want to have that 8 electrons, all the bondings happen. Now some of them, for example, NaCl. In case of sodium chloride, what happens is from Na, right? Check it out here. If this is Na and this is your Cl, so what happens is from Na, actually a transfer of electron happens. An electron actually gets transferred here, and that is why it forms something called as ionic bond, okay? Now, there is also a possibility where, for example, hydrogen and hydrogen. So hydrogen and hydrogen, what they do is, hydrogen provides one electron here, and this hydrogen will also provide one electron. Together, they will form a duplet. Okay, so hydrogen only has hydrogen has an exception. Helium also has an exception because helium does not complete its octet. It doesn't have 8 electrons. It has 2. That's called as duplet. So either duplet or octet. That's the only thing they want to attain, right? So hydrogen wants to attain the duplet. It shares the electron and it forms a covalent bond, okay? It forms a covalent bond. So basically, if I have to tell you, ionic bond is transfer of electron, covalent bond is sharing, okay? This is sharing, right? This is sharing, and this is a full-on transfer that happens here. Like one electron is given away, right? Okay, all right, get it? Okay, so that's how the bond is forming. And because they have both attained their octet or the duplet, they are stable. Correct? That's what Lewis said. Okay, easy peasy. Now Lewis said that because we are only talking about the outermost electron, that means we can also have a symbol with the outermost electron. Yes, we are not complicating things. We're making things easier, right? So Lewis came up with symbol where he used to only put a dot and tell you that these many electrons are present in the outermost shell. You take a look at it. Take a look at it. Here, see, there is hydrogen here and one dot. Lithium, one dot. Sodium, one dot. Potassium, one dot. Now, what does it mean? It means that all of them have one electron in the last shell. Now, take a look at beryllium, magnesium, calcium. All of them have two electrons. That means 2 electrons in the last shell. Boron and aluminium, 3 electrons in the last shell. Carbon and silicon, 4 electrons in the last. So you get my point, right? Now take a look at the helium, neon, and argon. Okay, if you count 1, 2, 3, 4, 5, 6, 7, 8, there are 8 electrons. That means stable octet. They already have it. So what Lewis did was, in the formation of a molecule, he said that only outer shell electrons take part, and they are called as valence electrons. Yes, what are valence electrons? These are the valence electrons, whatever is there in the last shell. The inner shell electrons are well protected, so they're generally not involved in the combination process at all. So he introduced this simple notation, which we like to call it as a Lewis symbol today, okay? So the number of dots that you see here around the symbol, it represents the number of valence electrons. Now, do you think that here it is a 5? What is the valency? Valence electrons is 5. Yes, what is the valency? The valency here would be, my dear student, what you have to do is 8 minus 5. So that means it is 3. 1, 2, 3, 4, 5, right? Valency is 3, valence electron is 5. Get my point? Yes, get my point? Now, do you notice that Lewis was only talking about electron? So that means that, of course, we can call this whole thing as electronic theory of chemical bonding, correct? So he's also called it as electronic theory of chemical bonding. Electronic theory of chemical bonding. Okay, that's what he spoke about. That's what, I mean, people also started calling this as electronic theory of chemical bonding. Understood? Yes, got it? Great. Now, what is octet rule? To attain this octet rule, to attain that 8 number of electrons, octet rule is basically nothing but attaining 8 electrons in the last shell, right? How can they attain this 8 electrons in the last shell? Either they will do transferring, like how you see in case of NaCl, transfer of electron is happening there, and that's how they're forming bond. So transfer of valence electron from one atom to another, what do we call it? We call this to be ionic bond. Am I right? Yes. Or there is sharing of valence electron, like you see in case of hydrogen, which is called as your covalent bond. Okay, this is your covalent bond. Now let me explain this with another example here. Okay, I think this will be making more sense to you. Take a look at this here. See how this dog had one bone. Yes, this dog, the yellow dog, had one bone. It came and it gave the bone to this white dog, and now the white dog has two bones, but this one doesn't have any bone. So that's your ionic bond. Full on transfer happened. It came and gave the bone away to the white dog, right? That's your ionic bond, NaCl. Now look here. Yes, both of them are 2 yellow dogs. Both of them had one bone. This one came and gave this, and now both of them are holding on to the bone. See, both of them are holding on to the bone. Yes, and that is your covalent bond. Make sense? Make sense? Nonsense, everybody? Yes, NaCl is ionic bond. Cl2 is your covalent bond. Correct? We get it? Okay. All right then. Now moving on from here, let's understand how to make the Lewis dot structure. Okay. So there are 5 points. There are 5 points to make the Lewis dot structure. Very easy. You count the total number of valence electrons. You identify the central atom. You draw the skeleton and join them by single bond. You assign remaining number of electrons as lone pairs, and you convert lone pairs into double or triple bond to complete octet of all atoms. Understood? Should I move ahead? Of course not, right? So let me explain this. Let's take the example of carbon dioxide. Okay, very easy, very simple. CO2. See, count the total number of valence electrons. Now, carbon has 4 electrons in the outermost shell, so let's write 4 here. Plus, oxygen has 6 electrons in the last shell. So 2 into 6 is 12. 12, 13, 14, 15, 16. 16 electrons are there. Identify the central atom. I can clearly see that there is only one carbon and there are 2 oxygens. So what I'm going to do is, this is my central atom. I have drawn the skeleton and I've joined them by single bond, right? I've done this, okay? Now, what is the remaining? See, here, carbon would have given 1 electron, right? Take a look at it. See, carbon is giving 1 electron here, carbon is giving 1 electron here. Now, oxygen is going to give you 1 electron here. Oxygen is again going to give you here 1 electron. So that means total 4 electrons we have used up, right? 4 electrons we have used up. So 16 minus 4 is equal to 12. 12 electrons are remaining. So how am I going to give this 12 electrons? See, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now, the rule says that convert the lone pairs. What is this lone pair, Baba? Lone pair is basically 2 electrons. 2 electrons possessed by an atom not involved in a bond, okay? Not involved in a bond. So these are called as lone pairs. So oxygen has 3 lone pairs here, oxygen has 3 lone pairs here. Now what we will do is we will convert this lone pair into a double bond. So here this bond will come as a double bond and this bond will come as a double bond. That means my final structure, my final Lewis dot structure will be C double bond O, C double bond O, and the remaining 1, 2, 3, 4, 1, 2, 3, 4 electrons I have drawn. And this is, my dear student, this is my final Lewis dot structure. Okay, all right. Now we come to a term called formal charge. What is this formal charge? But you have to understand that actually, there are different Lewis structure that is possible. For example, if I take the example of ozone, right? Ozone can exist like, what is it? Ozone is O3. So don't you think it can exist like this? Okay, it can exist like this here. Okay, all right. Yes, these three, there can be double bond here, or there can be a double bond here and a single bond here. Both of them are possible, right? Both of them are possible, correct? So these are called as canonical forms. These are called as your canonical forms. But in reality, it is seen that actually none of them exist. The canonical forms don't exist. Actually, what exists is there is something like this. So basically, it's not two double bonds. It's not two double bonds, but it is rather 1.5, 1.5. So the bond length, we will study what is bond length, but you get it, right? The length of the bond. The bond length is between a single bond and a double bond. The bond length is not a correct measurement of a single bond, neither it is a correct measurement of double bond. So it's between them. So now when you have these three structures, how will you choose which one is the actual structure? Which one is the actual Lewis structure? Problem, right? So to steer away from this problem, okay, what we do is we introduce something called as formal charge. Basically, whichever structure has the least formal charge, that will be your actual Lewis dot structure. Okay. So let's again take the example of CO2. Let's take the example of CO2. For CO2, the structure was C double bond O here, C double bond O here, 1, 2, and 3, 4. 1, 2, 3, 4. 4 electrons that are remaining with oxygen, that is 2 lone pair. So what is the definition? The definition says difference between the number of valence electrons of that atom in an isolated or free state and the number of electrons assigned to that atom in the Lewis structure. Too much. Understand this. See, here I have made it easier. Formal charge is equal to number of valence electrons in the free or neutral state. How many number of electrons does carbon have? 4. Minus number of lone pairs. Does carbon have any lone pair? 0. No lone pair. And then half of electrons involved in bonds. See, 1, 2, 3, 4. 2 from oxygen, 2 from carbon. So 4 this side, 2 from carbon, 2 from oxygen, 4 this side. That means 8 electrons are participating in this bond formation. So that means 2 into 4 is 8. So 4 minus 4 is equal to 0. Formal charge is 0. Hence, this Lewis structure makes sense to us. Okay. So generally, the lowest energy structure is the one with the smallest formal charge, and that is your Lewis structure. Got it? Clear? Yes? No doubts here? Crystal clear? Easy peasy biryani tasting? Amazing. Let's move on. Okay. Let's move on. So actually what happened is the octet rule, it dictates the atom are more stable when their valence shells are filled with 8 electrons. We have understood this, right? And this rule is based on the chemical inertness of the noble gases, right? We saw that the noble gases are inert. The noble gases don't like to mingle with someone else because they have 8 electrons. So based on that, we gave this rule, right? But there was limitation, obviously. There was limitation. What was the limitation? The incomplete octet of the central atom. Take a look at it. See, LiCN. LiCN. Now, Li has only 1 electron in its outermost shell, right? Li has only 1 electron in its outermost shell. But Cl is in the 17th group, so there are 7 electrons in the outermost shell. So see, 1, 2, 3, 4, 5, 6, and 7, right? So this electron, when it gets transferred here, the LiCl bond is formed. But do you see that is Li able to complete its octet? Is Li able to complete its octet? Cl is able to. Cl gets 8 electrons, definitely. But what about Li? No. Incomplete octet is not complete here. Now take a look at BeH2, right? See, Be, beryllium has how many? 2 electrons, right? Beryllium has 2 electrons, so 1 here, hydrogen, 1 here, hydrogen, 1, 2, 3, 4. Only 4 electrons are there in the valence shell. Incomplete octet. Incomplete octet happened. So what now? What now? Yes, so that was a limitation. Next what came up was odd electron molecules. Check out nitrogen, yes, NO and NO2, both are examples actually, but let me show you NO, okay? So nitrogen has how many? Nitrogen has basically 5 electrons, right? So that means that 1, 2, 3, 4 and 5, okay? This electron will be used up. Oxygen has 1, 2, 3, 4, 5 and 6, right? So here they have formed the bond. Now see, oxygen 1, 2, 3, 4, 5, 6, 7. 7 electron it is forming. 7 electron it has, no octet here, 7 electron. And here see 1, 2, 3, 4, 5, 6. 6 electron they are getting. How is it possible? See, that's not possible. Same like this for NO2 also. The third one, the expanded octet. Now what happened? More than 8 electrons came into the picture. This only happened when there are elements which have 3D orbitals, okay? Where there are 3D orbitals that are participating. Check out, example is PF5. Example is PF5, okay? So P is also in the F, yeah, I mean N1, so 5 electrons, right? So see here, 1, 2, 3, 4, 5, okay? Now check here, 1, 2, 3, 4, 5, 6, 7, 8, okay? Fluorine has its 8 electron definitely, but look at P. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electron. Phosphorus has 10 electrons. Expanded octet rule. You get my point? So these are the limitations of this octet rule. These are the limitation of the Purcell-Lewis approach to chemical bonding, and that's why we needed something else. Okay? What did we need? We need VSEPR theory, to which we will come later. But now let's understand the ionic or the electrovalent bond. My dear student, we understand that the ionic bond happens when there is a transfer of charge. That means if there is Na and if there is Cl, from Na, 1 electron is coming out of the atom and getting inside the chlorine, right? Right? Yes? In this case, there are 3 terms also that are used. Okay, 3 terms. 3 terms are ionization enthalpy, electron gain enthalpy, and lattice enthalpy. So what is ionization enthalpy? Ionization enthalpy is the energy required to take 1 electron away from an isolated gaseous atom, from an isolated gaseous atom is called your ionization enthalpy. Basically, if I have M, that is in gaseous state, if this is my atom, what I want to do is make it M plus, and I have taken one electron away. So this is my ionization enthalpy. All right, get it? Now, what is this electron gain enthalpy? What happened to chlorine? Chlorine accepted one electron, right? Yes. So when the atom is accepting an electron, it will release energy. See, understand it this way. Ionization enthalpy, I always give this example, right? So as a girl, I am shopaholic, right? I love shopping, obviously. I love it, right? Like I cannot stop. I cannot stop, really. I mean, if you see me coming to office, you will almost find me in new clothes every day because that's the amount I love shopping. But shh, you don't tell this to anyone, okay? Anyway, so basically what happened is, I have definitely prepared a cart in Myntra, I have prepared a cart in Urbanic, I have prepared a cart in Amazon, I have prepared a cart in Flipkart. Trust me, I swear to God, if I show you my cart, you will see that there is at least 5 to 10,000 rupees a cart that I have made and I've kept it. Now, obviously, I'm not going to shop because month end is almost coming and I can't do that, right? But if I want those things, right, what do I have to do? I have to lose some money from my pocket, right? I'll be losing out some money and only then I'll be getting those materials, isn't it? Yes. So basically, do you see, when you have to take an electron away, when you take an electron away, the atom needs some energy. Without the energy, the atom is not going to give its electron away, right? The very same way, if I want those clothes, I will have to give away some money. Without giving away the money, how am I going to get new clothes, Baba? I cannot, right? Do you think that Myntra, Amazon and Flipkart will be like, you like shopping, you take the clothes? Will they do that? No, that's what is happening. Now, if somebody, now understand this, that now if somebody says that, you know what, give me your clothes, I'll be like, you're crazy, or what? I'm not selling my clothes. I'm not giving away my clothes. And even if I am, I will require the amount that I paid for, right? And so you get my point, right? You get my point. So if I'm giving away my clothes, you must have seen, right? You know, your mom probably does it. She gives away her old clothes and then they give utensils. Yeah, utensils. Yes. So if she's releasing her old clothes, what is happening? There are new things that are coming into your house. That's what utensils. The very same way here, when an atom gains an electron, it gives away some energy. It releases some energy. So what is electron gain enthalpy? The amount of energy released by an isolated, and all of this happens in an isolated gaseous state. The atom should not be bonded, by the way. It should not be bonded, okay? So the amount of energy released by an isolated gaseous atom when an electron is pushed into it. All right, okay? So basically, this is actually negative in nature, okay? And if it is highly negative, that means that the bond formation is going to be easy. Highly negative, easier to gain electron, okay? Easier to gain electron. And this, if it is low, better. Low, easier for bond formation. Okay, you get my point? Now let's come to, what is it? Now let's come to lattice enthalpy. What is lattice enthalpy? So my dear student, you understand that when I say NaCl, I don't mean that there is only one atom of Na and one atom of Cl, right? It's probably NaCl, 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 everywhere. It's a lattice. It's a crystal lattice, correct? Yes. So lattice enthalpy means that the energy required to separate 1 mole of solid NaCl into 1 mole of solid Na plus in gaseous state and 1 mole of Cl minus gaseous state to infinite distance. We are separating them. We are breaking them apart. That is your lattice enthalpy. So let's write it down, okay? What is lattice enthalpy? The energy required to separate 1 mole of solid NaCl to 1 mole of Na plus in gaseous state and 1 mole of Cl minus gaseous state to an infinite distance. See, it should be infinite distance, and wait a second, let me explain this. Okay. So why do we write infinite distance? Why do we write infinite distance? Well, that's because if they are closer to each other, positive will attract negative, and what will happen? NaCl will form again. So you separate them to such a distance from where they cannot come back and form the lattice again. Okay, and that is why we say that it is infinite distance. Get my point? Okay. So what did I say? Obviously, the ionic bonds will be formed more easily between the elements which have comparatively low ionization for energy and highly negative electron gain enthalpy. Only then it will be easier to form the bond basically, right? Okay. Get my point? Great. Easy peasy, biryani tasty. Now that we have understood how the bond has formed, let's talk about some of the bond parameters. What is parameters? Like if I talk about myself, you will ask me, what's your height, what's your weight, what is the chashma power, right? So these are my parameters, isn't it? The same way, when we talk about a bond, there are certain characteristics, certain properties that we want to talk about the bond. So obviously bond length comes the first. Now, do you think that bond length, when you're talking about bond length, do you think that it's just a line? Actually, it's not. It's not a line. For our convenience, to make our life easier, we say that, it must be a line. It is not. It's not a line, okay? You know that electrons are in a cloud, right? All of that we studied in the structure of atom. It's like a wave, it's like a particle and blah, 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 all of that we did. So how can bond be a line only? Not possible, right? But anyway, what is bond length? Bond length is defined as the equilibrium distance between the nuclei of two bonded atoms. That means in a molecule. So let's say that we have a molecule here, right? We have a molecule, here is an atom, here is another atom. These two are bonded. This is your nuclei, this is your nuclei. Now from here to here, when you measure this distance, this D is your bond length, okay? This D becomes your bond length. Get my point? Yes. Now half of the bond length can be your covalent radius, correct? half of the bond length is going to be covalent radius. However, in van der Waals radius, what do we say? We say that it's non-bonded. It's an adjacent atom but not bonded, because van der Waals radius is for noble gases, right? Yes. So here is something that you have to know. You have to know that the covalent radius is measured approximately as the radius of an atom's core. Radius of an atom's core, yes, which is in contact with the core of another adjacent atom. That's your covalent radius. But in case of the van der Waals radius, it represents the overall size of the atom, which includes its valence shell in a non-bonded situation. Agreed? Agreed? Yes? Got it? Okay. Now what is bond angle? Once again, it's not a line. Then how are we finding out the angle? Angle can be between two lines. No, that's what we have learned, isn't it? 90 degree, 120 degree, this and that, and all of that angle. In mathematics, we know that it's between two lines. How come we are measuring it here? And here what we're saying is the angle between the orbitals. The orbitals, if it is d orbital, in the d orbital and between a p orbital, right? Okay. So angle between the orbitals that contain the bonding electron pairs around the central metal atom in a molecule or a complex ion, that's your bond angle. Gotcha? Clear? Awesome. Next one is, see, bond enthalpy. What is bond enthalpy? The energy required to break a bond. Okay, the energy that is required to break a bond, that's called as bond enthalpy. Now what is bond order? Bond order is basically the number of bonds between the two atoms. If it is 1, then single bond. If it is 2, double bond. If it is 3, triple bond. If it is 0, the molecule does not exist. Getting my point? If it is 0, the molecule does not exist. You get my point? Yes. Now here is something that you need to know. Okay, so isoelectronic molecules. What do we mean by isoelectronic molecules? That means the molecules have same number of electrons. The molecules have same number of electrons. They are called as isoelectronic molecules. So isoelectronic molecules and isoelectronic ions, they have identical bond order. What do we mean by identical bond order? Identical bond order means they have same bond order. Obviously, they have the same number of electrons. Now, how will they bond? They will bond also in the same way. So obviously, they have identical bond order, right? Now, if the bond order increases, bond enthalpy also increases. If the bond order increases, then, actually, you tell me. If I'm holding like this, single bond, I can easily break it, right? But if there is two bond, if there is double bond, it will require a little more energy to break. If it is triple bond, it will require a little more energy to break, right? Yes, everybody. Are you getting my point? So you see that whenever the bond order increases, bond enthalpy also increases. The next point says bond length decreases. What do you mean by that? See, check it out. If I keep my hand like this here, see, I'm touching the board here, okay? I'm touching the board and I can be as far as possible, right? I can be very far away. But if I have to increase the bond, now I'll be like this. Now see, I'm a little closer to the board. Now if I may have to make a triple bond, I will have to use my leg. I'll have to come even more closer. You get my point? So what is happening? Bond length decreases. As you increase the bond order, the bond length decreases. Okay? Alright? Get my point? Okay? Okay. Now let's understand resonance structure. You know what is resonance structure? I spoke to you about ozone, right? Check it out. See what ozone does? Yes. Here, 1, 2, 3, 3 oxygen are there. Now you see, either they can have a double bond here or they can have a double bond here. Right? So basically what happens is the electron can move. Delocalization of electron. The electron does not stick to one place. The electron can move from one place to another. And when it is moving, what happens? It can either show this structure or it can show that structure. So the definition of resonance structure is the phenomenon of existence of a molecule in many structures. That is, a molecule can exist in 2 or 3 structures. Why? Because of delocalization of electron. The electron moves, hence you get 2 or 3 different structures. Get my point? Yeah. Okay. Actually, now all this time we were talking about bond. When we spoke about ionic bond and covalent bond, right? We said that either the transfer of electron happens or sharing of electron happens. Transfer means ionic and sharing means covalent. But what if I told you that in reality it was found that there is no bond or there is no compound that is either completely covalent or it is completely ionic? It was not found. Every molecule had some percentage of ionic character and it had some percentage of covalent character. But how is this formed? How is this formed? Now we came to this thing called as bond polarity. There is something called as bond polarity. Actually, let's not read the definition now, okay? Let me give you a story. So you all have TV in your house, right? You all watch TV, right? And I'm pretty sure that most of you also have a sibling. You either have a brother or a sister, right? Yeah. So let me give you an example of me and my brother. I have a younger brother. He's still studying, yeah? And he is with my parents in Guwahati. So when we were younger, my brother and I used to love watching the CID, you know, that ACP Pradyuman and Darwaza Tod Do. So we used to watch this. And there were times when we both wanted to watch the same CID show. So obviously at that time, when we took the remote, there was no fight between us. And we both are like very calmly and nicely, we're like, you know, we're being like couch potatoes and we are watching the CID. But then we started to grow up a little bit, right? And when we started to grow up, now I started becoming a little cool kid. I started listening to all these English songs, right? You know, like Linkin Park and Taylor Swift and Enrique and all of that, right? But my brother was still younger than me, right? He's what, 5-6 years old, younger than me. So he still wanted to watch CID. Now when I grew up and I wanted to watch something, so both of us started fighting like, no, I want the remote, no, I want the remote, no, I want the remote, no, I want the remote. We kept doing this. Now certain times I snatched the remote from him and I could watch the, you know, the English songs or the English movies that I was so fond of. And certain times we fought and he won the remote, so he took the remote and he started watching CID. So you get my point, what is happening? Certain times I was happy, certain times he was happy, but we were both not happy when we started growing up. But before that, when we were younger, we were non-polar, right? Our bonding was very nice because both of us were doing the same thing. So the very same way, understand this, when covalent bond is formed between two similar atoms when they're bonding, and the shared pair of electron is equally attracted by the two atoms, just like how CID was equally attractive for both of us, me and my brother. And as a result, the remote was situated exactly between the both of us. We were like, sound brow, let's increase the volume. We were increasing the volume. The sound is too much, mom will get up, so decrease the volume. We were doing that, both of us together. So this time, the bond that was formed was what? Non-polar covalent bond, right? This was non-polar covalent bond. But when we grew up, then what happened? Now when the covalent bond is formed, okay, let's write it down. Yeah, now let's write it down. Here, what we have to write is when covalent bond is formed is formed between two dissimilar atoms. The shared pair of electron is not equally attracted by the atoms, by the two atoms. As a result, the electron pair is situated closer to one of the atoms. This is called as polar covalent bond. This is polar covalent bond. You get my point? Yes. Okay. So now understand this. So when there are two charges, yes. Now what happened? I snatched the remote from my brother towards me, right? I snatched the remote. Here what is happening? Basically there are two charges, right? Imagine this. When I snatched the remote, let's consider the remote to be an electron. What happened to me? I became negatively charged. And because I snatched away the remote, my brother was positive. So equal and opposite charge when they have a distance, when they're separated by a distance, what do you call it? Dipole moment. Yes. Equal and opposite charge separated by a distance is called dipole moment. Am I right, everybody? Yes, guys, correct? Yes. Now here comes this is your mu is equal to q into d. This is how you calculate dipole moment. And the unit of dipole moment, as you all know, it is dBi. What is it? dBi. Okay. All right. Now here you have something called as BF3. This is the structure of BF3. Now you have to understand, my dear student, that in dipole moment is a vector quantity, right? It's a vector quantity. So here what happens? Some of the dipole moments of various bonds happen. Yes. Now it is not only dependent on what exactly the dipole moment is, but also the spatial arrangement of the molecule. Yes. Now understand this. In case of BF3, so this vector and this vector, the resultant will be this side. Some of the two vectors here, resultant will be this side. Now when there is this vector here and this vector here, this will be equal in opposite. So the dipole moment would be zero. Dipole moment would be zero. Are you understanding? Yes. Yes. Are you getting my point? Correct, everybody? Yes. So what did I say? That in case of a polyatomic molecule, the dipole moment does not depend upon the individual dipole moment of bonds. It does not depend upon this dipole bond or this dipole bond. It depends upon the spatial arrangement of various bonds in the molecules. Now, because how they are arranged like this in the space, so this plus this resultant will be this side, and this is equally opposite to this, so the dipole moment will be zero. Get it? Understood? Okay, great. All right, now moving on, there is something else also. Now we come to something called as Fajans rule. Everybody, in India, a lot of people call it Fajans rule. Please understand, it's not Fajans rule. It's called as Fajans rule. J is pronounced as Y. Okay, Fajans rule. Before we get to Fajans rule, you have to understand the polarizing power and the power of, polarizability. What are these terms? Let's understand, Bacha. So understand that there is a cation. The cation is basically the positive charged ion, right? And the anion is negatively charged ion. So the cation, let's say, is coming to the anion, right? Yes. Now imagine that the cation is very charged. The cation has a lot of positive charge. So the moment it has a lot of positive charge, what will happen from the anion? Many negative charge will be like, oh, go opposite, attract. They will start getting attracted. So this one will get distorted. The anion shape will get distorted. The anion will be like, oh, negative, let's go. Right? Yes. Sorry, positive, let's go. Yes. So basically what is happening is the cation has a polarizing power. The cation is distorting the shape of the anion. It's calling it towards it like, come, let's neutralize each other. Are you understanding? Yes. So the power of cation to polarize the anion is called polarizing power. And what is polarizability? The tendency of anion to get characterized. Now the anion can also be like, I don't want to be polarized. Then what? The tendency of the polarizability is less. If the anion is also like super excited, whoa, let's get polarized. If it's treating like this, then the polarizability is more. Are you understanding? So the tendency of anion to get polarized is called polarizability. Now you have to understand that greater is the polarization. If the cation can polarize the anion and more number of charges are getting neutralized, then the ionic character is less, because now they're forming a covalent bond, right? Covalent bond, sharing is happening. So this positive came, this negative came here, they neutralized each other. No ionic. For ion, you need the charges, right? For ionic bond to exist, you need the positive charge or the negative charge. It's not there, only they have neutralized. Now the covalent character is more, ionic character is less. But if that's not the case, then the ionic character is more, covalent character is less. Understand it with this example, yeah? Here is a polar covalent, like this thing. How this dog came, but this one is a Great Dane, right? This one is a Great Dane, it's a bigger dog. What it did was, it pulled the bone towards itself. See, it pulled the bone towards itself. Are you understanding? Exactly. See, here also hydrogen and fluorine. See, hydrogen had one electron. So what fluorine did was fluorine pulled the electron towards its more. Hydrogen could not do that. Hydrogen could not pull electrons from fluorine though. But fluorine did, because fluorine is more electronegative. Fluorine wants to gain electron easily, right? Because it wants to attain the octet rule. Yeah? Yes. So here what is happening? More polarization of fluorine. Fluorine can polarize the hydrogen atom. Getting my point? Now that you have understood all of these, now let's understand what Fajans said. Fajans said that, okay? Fajans said that the smaller the size of the cation, if the cation is very small, then and if the anion size is big, then the covalent character of an ionic bond will be more. Getting my point? Cation is small, anion is big. Then the bond that is created, of course it's ionic bond, but the covalent character is more here. Okay? Yes. Now, second point he said was greater the charge on the cation and greater the covalent character of the ionic bond. If the cation has a lot of charge, let's say it's 2 plus, it's 3 plus. If the cation is 2 plus, 3 plus, then what will happen? The covalent character of the ionic bond will be more. Basically, it will be leaning towards covalent bond more. And then for cations of the same size and charge, imagine that there is one cation, there is another cation. Same size, same charge, 2 plus, 2 plus. Now, which one will you consider more polarized? Which one do you think that has more polarizing power? Which one will be able to polarize more? Now comes this line, understand this, the electronic configuration that has n minus 1 d to the power n is 0. That means it has to be a transition metal. If it is a transition metal, then the polarizing power will be more. Yes, then the polarizing power will be more. But if it is a alkali or alkaline earth metal, for example, Ns2Np6, if it is a alkali or alkaline earth metal, then the polarizing power will be less than the transition metal. You get it? Yes, it will be less than the transition metal. So what is the gist of it? The gist of it, Fayan said that just as all the covalent bonds have some partial ionic character, the ionic bonds also have some partial covalent character. And this partial covalent character of ionic bond was discussed by Fayan's rule. Getting it? Yes. Now Fayan's rule, very important. Please do remember SCLA. SCLA. This is the first rule. SCLA. Like UCLA, University of California, Los Angeles. Like that, you remember SCLA, School of Los Angeles. Let's say, okay, School of California, Los Angeles. Basically, that means that what? Smaller cation, large anion, polarizing power more. Remember this. It's very important. Remember this. Even for your S block, for your P block, for your DNF block, this is very important. The first rule you've got to remember it. Okay. All right, everybody. Now, guys, let's move on towards our IIT JEE mains and advanced questions. So here comes BSEPR theory. By the way, guys, we do have questions. This was very easy. This was only board level, so hence I did not do much question. And also, of course, we will have some problem solving classes as well. But first, let's read this. So BSEPR theory. What happens in BSEPR theory? BSEPR theory. You know what is the full form of BSEPR theory? Yes or no? No? Yes? Let me tell you. BSEPR theory is valence shell. Valence shell. Electron pair repulsion theory. Okay, the answer is right here. What is BSEPR theory? Somebody asks you. The answer is right here. Answer says that valence shell, last shell in which the electron is, valence shell, they will come closer. But electron and electron are the ones they form the bond, but they are both of the same charge. And we know from the very beginning of our education that that like charges repel each other. So an electron pair and an electron pair, they will repel. That's it. Valence shell, last electron shell. They will come together to form bond, but electron and electron are going to form the bond. But both of them are what? Like charges. Like charges will repel each other, and that is our VSEPR theory. In short form, we also call it Vesper theory. Okay, all right, so we understood this. Now, Vesper theory says that the shape of a molecule, what is going to be the shape of a molecule? The shape of a molecule will actually depend upon the number of valence shell electron pair, bonded or non-bonded, around the central atom. So if you have an atom, in the atom, how many valence shell electrons are there? Are they bonded? Are they non-bonded? Based on that, your molecule shape, you can find out. Okay? Understanding this much? This is the first point. First point is done. What is the first point? The shape of the molecule. What will be the shape of the molecule? Will depend on how many last shell, how many electrons are there in the last shell. Are they bonded? Are they non-bonded? That's it. Okay? Second one says that the pairs of electron in the valence shell, they will repel one another, because obviously electron clouds, all of them are negatively charged, and we know that like charges repel each other, right? Unlike charges attract each other, right? We know this from the very, very junior grade, right? Now it says that these pair of electrons, they occupy such positions so that the repulsion is minimum. For example, imagine if I'm getting a shock from this, the board. What will I do? I will not touch it, right? I will stay away. Now, in such a position that I am still visible, the board is still visible, and I'm not touching it, so I'm not getting a shock of my life. This is my position. At this position, the shock I'm not getting, I've minimized the shock, and I'm also visible in the camera. So right here I am. This is my position, and this is deciding how I'm standing in the class, right? Exactly. This is what it said. It said that the pair of electrons, they tend to occupy, they stay in such positions where the space, in the space, they tend to occupy such position in space where the repulsion between the electron cloud is minimum. Okay? Yes? And they can maximize the distance between them. There should be like maximum distance, less repulsion. They're happy. Got it? You know what? BSEPR theory, it was actually, I think, proposed by someone called as Sidgwick and Powell, if I'm not wrong. I think it was proposed by Sidgwick and Powell. First time it was proposed by Sidgwick and Powell. Second time, I think it was given by who gave it? Was it Nyholm and Gillespie? Yes, they developed it. Nyholm. I hope I've written the right spelling. If you want, you can check it from your NCERT. I think you'll find it. Okay. So Nyholm and Gillespie, I think about I remembered it as 10 years after our independence, 1957. 1947 is when we got independence, right? 1957 is when they developed it, and 1940 was when Sidgwick and Powell had given it up. I mean, they said that this is how it is going to look like. Okay. So moving on now. Now what happened is the valence shell is taken in a sphere. So you say that the last shell is actually a sphere. Okay. The last shell is actually a sphere. All right. And with the electron pairs localizing on the spherical surface. So what happens is if the electron pair is here, let's say here, and there is another electron cloud that is here. Okay. Let's say that here also you have an electron. So what will this do? This one will delocalize and go here. This one will move from here to here because maximum distance. Not even maximum distance. To make maximum distance, it will actually go here. It will actually go here. Maximum distance it wants, right? So it will delocalize. It will move away from that electron. Okay, both of them will do what? Now this one also won't stay here. This will also delocalize and come here. They will say that, Baba, maximum distance, no worries. I don't want to fight with you. At maximum distance from one another, they will survive. Okay. Now a multiple bond. In this case, if there are double bond or triple bond, you are not going to consider them as double bond or triple bond. What will you do? You will consider them, okay, 2 or 3 electron pair of multiple bond. You will treat them as a single super pair. No worries. You have multiple bond. You have double bond. Doesn't matter. Here you are going to take them as one single super pair. Got it? Please listen to this. Don't you think that this can be a limitation later on? It will be. It will be a limitation. But you understand, right? Here, what are we saying? Multiple bonds are treated as single super pair. Okay. Now, if there are 2 or more resonance structure, in that case, you can use VSEPR theory and you can apply it to any such structure and find the shape. How are they going to exist? Which actually is the structure? You can easily find it from VSEPR theory. Make sense? Nonsense? Make sense, right? In case of VSEPR theory, there's another thing you have to understand, that a lone pair repulsion. You know what is lone pair, right? Those which are non-bonded. So a lone pair repulsion is maximum. A lone pair, the non-bonded one. So understand this, my dear student. If you are in a family, do you fight a lot? No. But single people in the hostel, if you put all of it, when you all go to hostel, what will you do? You will do tandem, right? You will fight, you will have fun, you will go out, you will bunk classes, you will go out of the hostel campus at night and all of this. But can you do the same thing at home also? You can, but you will still be scared that, yeah, if mom and dad get out, then you will get the shock of the life, right? Yes. So understand that when you are lone pair, when you are not bonded to anyone in the hostel, the fight, the fun, everything will be more, right? But if there is a lone pair and a bond pair, if you have, let's say, there is a lone pair like you, and there is also a bond pair. Let's say that 2 hostels, a married couple hostel and your hostel where all the single people are there, right? Between them, you will not fight so much. You will not have fight so much. You can also not have fun so much. Why? Because the moment you start shouting, they will be like, call to warden, warden, this hostel is shouting too much. That will happen. So you cannot have fun so much. You cannot also have, you cannot fight so much also, because lone pair, bond pair, warden will come and they will sort it out. Correct? Yes. So lone pair, bond pair will happen here. Yes. And then finally, what happens? Now imagine that you all are in a family. What will happen? The fight, fun, everything is less here because you are bonded, right? Sometimes you want to do something on a Sunday, but let's just say that your mom or your dad, they have work, they cannot take you. So what will happen? Bond pair fun will be, like, I'm not saying that it is, but just an example. Yeah, just an example. Okay, just say, please don't blast on me and say this, ma'am, you're giving a stereotypical example. Just an example. Okay. All right, everybody. So understand, this is the gist of your VECPR theory. Easy peasy biryani tasty. Looking like it? Great. Crystal clear? Yes. Do write down some la 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 or EPBT in the comment section so that I know that you all are understanding this. Okay. All right, guys. Moving on then. Now coming to VECPR theory, understand this. That so what happens is, take a look at it. Here you have a lone pair. Here you have a lone pair. See, this lone pair, it has pushed the bond pair together. But because bond pair and bond pair repulsion is less, they can exist with a very small bond angle also, 104.5 degree. They can exist very nicely. Okay. But here do you see the angle is much more? Why? Because bond pair can push because lone pair can push the bond pair a little more, but bond pair repulsion is less. But imagine if you have 2 lone pair now. Imagine if you have 2 lone pair. Do you think that it will be like this? Actually, it will be even more further away. Okay. It will be even more further away. It will be even more further away, and these two will come closer. These two will come closer. So the lone pair repulsion will be maximum. Then it will be lone pair bond pair, and the bond pair repulsion is the least. Okay, it is the least. Are you getting it? Yes. For the prediction of geometrical shapes of molecules with the help of VCPR theory, it is always convenient. It will always be easier for you if you divide the molecule in 2 categories. How? What are the categories? Molecule in which the central atom has no lone pair. There are 2 cases. Okay, 2 cases. Let me write down. What did I say? I said that molecule in which there is no lone pair. Molecule in which 0 lone pair. And molecule with lone pair. Okay, so if we divide it into these 2 categories, it becomes a little easier for us to find the shapes. So shall we check out now what shapes are we getting? Yes, how the molecules are going to look like. Chal, let's go. So geometry in which there is no lone pair. There are no lone pair of electrons in the central atom. Okay, the central atom, whatever electrons it had already shared. Everything is bonded. No lone pair at all. So take a look at it. Now, if the number of electron pairs are 2, there are 2 electron pairs. Okay, yes, arrangement of electron will be linear. Do you see? Yes, do you see everybody? Linear. This is A is your central atom. Here you have 1 atom. Here you have 1 atom. So the shape will be linear. Okay. Example is BeCl2. How do you draw BeCl2? Like this. BeCl. Beryllium has only 2 electrons. So 1 here, 1 here. Cl has 1, 2, 3, 4, 5, 6, and 7. 1, 2, 3, 4, 5, 6, and 7. Okay. This is your BeCl2. HgCl2 also you can draw the same way. Okay. Now, if number of electron pairs are 3 number of electron pair it is. If there are 3 electron pairs, then the shape is going to be trigonal planar. That means central atom at the center, A here, and then B, B, B. Okay. And then the angle, please do learn this also, 180 degree, 120 degree, okay, learn it. Now here is the example, BF3, okay, how do you draw BF3? See here, B, okay, F, and here will be another F. So boron has 3 electrons in the valence shell, 1, 2, 3, all the 3 are shared. Now fluorine has 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, and 7. Octet is also completed, okay. This is your BF3, got it? Now we come to 4 number of electron pairs. If there are 4 electron pairs, what will we do? If there are 4 electron pair, then the shape is going to be, molecular geometry is going to be tetrahedral, okay. For example, you have CH4. So C is your central atom. You will have H here, okay. Then you will have 1 H here. You will have another H here, and you will have another H here. So when you draw all of these, when you draw a line like this, you will find that this is like a tetrahedral. What is it? This is like a tetrahedral, okay. CH4 is tetrahedral. NH4 plus is also tetrahedral. Now you have 5 electron pairs, okay. 5 electron pairs. Now what do? Now your shape becomes trigonal bipyramidal. That means at the plane, here you have a trigonal, here you have a trigonal, one pyramid here, one pyramid at the bottom. So trigonal bipyramid. Okay, imagine it. Trigonal, here is a trigonal, and there is here is a pyramid on the top, here is a pyramid on the top. Okay, so that's your bipyramidal. Basically, it will be like this. Okay, see here, P. Okay, then you have a Cl here, you have a Cl here, and then you will have one Cl here, one Cl here, one Cl here. So you see how these three form a trigonal, then this forms a pyramid, this also forms a pyramid. Understood? Yes, it forms trigonal bipyramidal. If there are 6 electron pairs, it will form octahedral. What will it form? It will form octahedral. SF6 is an example of octahedral. Okay. Alright guys, making sense? Nonsense? Makes sense, right? Now if there are 7 electron pairs, it will be pentagonal bipyramidal. That means that, take a look at it. So how will I draw it? Is I here, okay. Then here will be 1F, here will be 1F, okay. Now what will I do is here 1F, here 1F, okay. Then 1, 2, 3, 4, 4 done, okay. Yes. Then here 1F, here 1F, and finally here also 1F. So basically when I close all of these, it will be like this. Does this not look like a pentagon? Yes. 1, 2, 3, 4, 5, 5 sides. And then from here, you will see that this goes and becomes like a pyramid. And from here, this goes and this becomes like a pyramid. So it will be pentagonal bipyramidal. Got it? Got it, everybody? Understand? Now let's take a look at in which the central atom has one or more lone pair. Okay. Now this time you have one or more lone pair. Okay. There are lone pair with the central atom basically. There are those electrons which are not bonded. Okay. There are remaining electrons that are not bonded to the other electrons. Okay. Now in this case, what if you have 2 bond pairs but 1 lone pair? Only 1 lone pair. So 2 plus 1, it becomes 3, right? Yes, the steric number is 3, no? 2 plus 1, 3, correct? Now check out my dear students. Yes, in this case also, what was the shape of the 3? Shape of 3 was trigonal planar. Here also it is going to be trigonal planar. Just hide this. When you hide the lone pair, you see that it is a trigonal planar. It is a triangle and it is in the same plane. Okay? Example is SO2 or O3, ozone or sulfur dioxide. Basically, if I have to make it, see how will I make it? It will be sulfur here. Sulfur has 2 lone pair here like this. Here will be 1 oxygen. Here will be 1 oxygen. SO2, hide this. What do you see? Trigonal planar. That's it. Bas. Okay? Now let's say that there are 3 bond pairs but 1 lone pair. Once again, when you hide this, how does it look like? This looks like a pyramid, right? This looks like a pyramid. So this you will call it as trigonal pyramidal. The shape is trigonal pyramidal, but arrangement of electron is tetrahedral. Here there are 2 terms, by the way, 2 terms. The shape is different, arrangement of electron is different. A little confusing, but we get it. How is the electron arranged? You see, here you have a lone pair, here you have a lone pair, but here is all the 3 bonded pair. Now if you take a look at it, how does it look like? See, this looks like a pyramid, right? It looks like a pyramid, isn't it? Yes. So we say that it is trigonal pyramidal, not bipyramidal, trigonal pyramidal. An example is NH3. Okay, example is NH3. Got it? All right. Then we go to the next one. Now we have 2 bond pairs, 2 lone pairs. Okay, 2 bond pair, 2 lone pairs. Steric number 4. Okay, steric number 4. That means see 3 plus 1, steric number 4 tetrahedral. 2 plus 2, steric number 4 tetrahedral. Steric 4 is tetrahedral. Remember, I will show you that chart also. I have that. So 4 is tetrahedral. Okay, but this time again, now close this 2 lone pair. What do you see? Bent shape. This one and this one is the same shape, right? See, this one and this one same bent shape. What is the example? H2O. Water has a bent shape. Water has a bent shape. Okay. All right, everybody, getting my point? Okay, great. Moving on from here now. Now, what if you have 4 bond pairs and 1 lone pair? This time it is 4 plus 1, 5. Steric number 4 means trigonal bipyramidal. Basically, you just close this. What shape do you see? When you close this, it actually looks like somewhat like this, right? B and B and then B and B, right? This, doesn't it look like a seesaw? And exactly what we wrote, seesaw. SF4, seesaw. Correct? Okay. Now we go to 3 plus 2. Once again, steric number is 5. Steric number 5, same arrangement. See, trigonal bipyramidal. But this time, the shape becomes T shape. See, close these 2 lone pair. What do you see? If you close these 2, T shape, and exactly what we have written here, T shape. ClF3 has T shape. Okay. This is also called as an interhalogen compound. Okay, what is it called as? Interhalogen compound. Halogen and halogen together, they are compounds. See, chlorine is a halogen, fluorine is a halogen. 2 halogen together, interhalogen compound. We will read about it in P block. Don't worry. Okay. Moving on. Now we have steric number 6. Steric number 6 octahedral. Remember, SF6. SF6 was also octahedral. Same here also. See, octahedral. 5 plus 1, 6. 6 becomes a square pyramidal. How square pyramidal? We are going to close this. What do you have? You have a square here. You have a square here, right? And you have a pyramid here. See, square pyramidal, correct? Absolutely. Yes. Now here what happens? 4 plus 2, 6. Steric number 6. Steric number 6 means octahedral. But this time you have 2 lone pairs. So close the lone pair. What do you have? You have square. All of it is in the same place. So square planar. Square planar. And the example is XeF4. Xenon tetrafluoride. XeF4. Okay. Now I have the chart here. Please do remember it. Steric number 2, linear. Steric number 3, trigonal planar. Steric number 4, tetrahedral. Steric number 5, trigonal bipyramidal. Steric number 6, octahedral. Steric number 7, pentagonal bipyramidal. So bipyramidal is only in 2 cases, 5 and 7. Okay. 5 and 7, 6 is octahedral, 4 is tetrahedral, 3 is trigonal planar, 2 is linear. Got it? Now let's solve the question. Shall we solve the question? Let's solve the question, everybody. Chalo. Which of the following has a geometry that is different from all the other 3 species? You are the same having the same geometry. Okay. Chalo. BF4, boron, right? Boron has 3 electrons, correct? Boron has 3 electrons, right? In the valence shell, B and then Al, right? Boron, aluminium, correct? Okay. But fluorine has, okay, so BF4, right? You have 4 here, you have 1 F here, you have 1 F here, you have 1 F here. And it says 4 minus. Minus, there is 1 electron extra. 1 electron extra, hence minus, so that means 4 electrons. All of them are done. Yes, so 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And this, I can write it as minus. Okay. Now, how many bond pairs do I have? I have 4 bond pairs. 4 bond pair, yes, 0 lone pair, yes, 4 bond pairs, that means steric number 4. Steric number 4 is what? Tetrahedral. Steric number 4 is a tetrahedral. sp3 hybridization, and this is a tetrahedral. Got it? Tetrahedral sp3 hybridization. Great. Now we have SO4 2 minus. Okay, so sulfur is our central atom. Sulfur has also 6 OS oxygen, and then sulfur has 6 oxygen, also has 6. So 4, let's do it. What it will do is it will form 2 double bond with oxygen here, 2 double bond with oxygen here. 6 plus 2, 8, right? So 1, 2, 3, 4, 5, 6, 7, 8. Right? Then you have 1 oxygen here, 1 oxygen here. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then here it will be 1, 2, 3, 4, 5, 6, 7, 8. Done? All done? Yes. Now this for here I can write it as 2 minus. Does it have any lone pair left? Does it have any lone pair left? 0. So once again you have 4 bond pair, 0 lone pair, 0 lone pair. Steric number 4 again. That means tetrahedral, everybody. Tetrahedral. Yes. All right, everybody. Tetrahedral. Once again, what do I write? sp3 hybridization. Correct. Great. For XeF4, let's do it. For XeF4, let's do it. Okay. Xenon. Xenon has how many? Xenon has 8 electrons, right? So that means 1, 2, 3, 4. Okay. Then here, let's do F. Okay. All right. So that means there will be 2 lone pairs here, and 1, 2, 3, 4. 4 bond pairs. So 4 BP and 0 I wrote again. 2 LP. 4 BP, 2 LP. Steric number is 6. 6 here. That means that it will be, look at this. This will be square planar, right? This will be square planar. Square planar. Okay. The steric number 6 should be octahedral, but this is square planar. All right. So that means this is the case, my dear student. pH4 plus will again be, take a look at it. P, it will be P, right? pH4 plus. P has actually 5 valence electrons, but it is 4 plus. I mean, pH4 plus. So that means 1 electron is gone. It will be H here, H here, H here. And then together you can just write plus. So this will also be tetrahedral. Answer is XeF4. See, correct only. Correct, we did it right only. Yeah. By the way, in this case, what is the hybridization? Hybridization will be sp3 and d2. Yes, sp3 d2 hybridization. Okay. Chalo. All right, guys. Moving on. Then, the solution is here also. This is a cleaner diagram. If you want, you can check it out. Chalo. Now we have PCl4 plus, PCl4 minus, and AsCl5. Chalo. What do we have? We have PCl4 plus, PCl4 minus, and we have AsCl5, right? AsCl5, PCl4 plus, PCl4 minus. Chalo, let's draw it. So phosphorus has how many? P has 5 valence electrons, but it is plus. It is plus, so 1 electron gone. That means that we can write it as, how can we write it? It will be Cl, 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 and Cl. Together here, let's write plus here. Yes, so this is what? This will be tetrahedral. This will be tetrahedral. PCl4 minus, 5 electrons it already has, but here it will be extra. So let's write it this. Let's write it like this, okay? This will be there, and then Cl4, right? So Cl, 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 and Cl. How does this look like? This looks like a seesaw shape. Seesaw shape. Obviously, it can be a little better, but come on. I'm not this thing, okay? I'm not Einstein. Not Einstein, sorry. I'm not Pablo Picasso. I can't draw that well. Okay? All right. So this means that this is PCl4 minus. Okay? Now we have As. As will have how much? Astatine. No, not astatine. Sorry, arsenic. Right? Yes? AsCl5. It has only 5. So that means that it will be AsCl5. Okay, Cl5. So like this. Cl, 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 Cl. 1, 2, 3, 4, 5. So this will be, my dear students, trigonal bipyramidal. Yes? What will it be? Trigonal bipyramidal. Alright. So that means that tetrahedral, seesaw, and trigonal bipyramidal, option B is the correct one. Easy peasy. Biryani tasty. Makes sense? Nonsense. Makes sense, right? Great. Here is the better, this thing, okay? Better scenario of it here. Okay. Chalo then. Now let's move on towards something called as hybridization. Obviously, VSEPR theory also did not make much sense at certain point because there was some limitation. So now we say that hybridization. What is hybrid? Hybrid, you know, right? What is hybrid, my dear students? Yeah. Don't we do that like we pluck like rose plant and then we mix it with some mix it with jasmine and we create something out of it which smells like rose also and jasmine also, and the flower looks a little different, right? We take some cabbage and then we mix it with broccoli and maybe make something else. I mean, that's what is hybrid, right? Where we mix two things, isn't it? We mix two things and we get something else. That's a hybrid. So same thing like that. Use the same analogy and bring it to your chemistry. What do you think? Here what we are doing is, obviously we are not mixing dog and wolf and cabbage and broccoli and rose and jasmine. Here we are mixing orbitals. So d orbital has more energy, p orbital has less energy, s has even more less energy, right? How about let's bring all of them together? Let's bring all of them together. Yes, they have slightly different energies. So we are going to bring them all together. We are intermixing them. We are going to mix them all together. Now what happens is a little bit from p goes into s and a little bit from d goes into p. So a redistribution of their energies happen. Right? What is happening? A redistribution of energies are going to happen here, and then they form a new set of orbitals where they have equivalent energies and shape. Now this time they have equivalent energies and shape. The energy and the shape is similar. Here what is happening, see, this is an s orbital, this is a p orbital, together they are mixing. Now you have together sp hybrid orbital. What do you have? You have sp hybrid orbital. And s atomic orbital and p atomic orbital, they intermix together and they formed sp hybridization, which is why you saw sp3d2 hybridization, sp3 hybridization, sp2 hybridization. Why do we use the word hybridization? That means that we have intermixed them, we have redistributed their energy, and we got something where our energy is equivalent and the shape is also same now. Yes. Now let's talk about the salient features, the characteristic of hybridization. What are we getting out of it? What are we getting out of hybridization? The number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. the number of hybrid orbitals is equal to the number of atomic orbitals that get hybridized. Understanding? Number of hybrid orbitals means, let's say that 1 plus 1 plus 1. What will we get? We will get 3 atomic orbitals. 1 plus 1 plus 1 is what? 3, right? Now you will be getting 3 atomic orbitals that get hybridized. 3 atomic orbitals got hybridized, okay? The hybridized orbitals, they are always equivalent in energy and shape. The shape will look same. Their energies will be same. Getting my point? Yes? Getting my point? Okay. Now, the hybrid orbitals are more effective in forming a stable bonds than the pure atomic orbitals. So sometimes what we have seen is, even in nature, right? People usually say that if your DNA gets more mutant, right? If you have like, if you have variety in DNA, so if your DNAs have got hybridized, that means your survival, your survival, how do I say, survival of the fittest is what Darwin said. So they say that you are more fit. Your chances of survival are more. The very same way here also what they're saying is, yes, when are they able to form a stable bond? When the orbitals are hybrid. Rather than a pure atomic orbital, when they are hybridized, when they have equivalent energy, when they have almost the same shape, that's when they are more stable. Getting my point? And then fourth salient feature is that these hybrid orbitals, they are directed in space in some preferred direction. They have their own set of direction that they want to follow. Some of them want to go this side, some of them want to go that side, some of them want to go this side, and it's okay. They have their own preferred direction where the minimum repulsion between electron pairs happen, and that is why a stable arrangement is obtained. Which is why the type of hybridization also indicates the geometry of the molecule. So now from the hybridization, you can find the geometry of the molecule. You getting my point? Yes. Now let's say types of hybridization. See, if S and P. If S and P orbitals get hybridized, you can have sp hybridization, sp2 hybridization, or sp3 hybridization. Okay. If there is sp and d hybrid, if there are 3 orbitals, sp and d, then you can have sp3d, sp3d2, and sp3d3. Okay. All right, everybody. Now finally, you know what? There is nothing that does not have an S character or P character. Every bond has certain percentage of S character, certain percentage of P character. So if you have S orbital only, then the percentage of S character will be 100%. If you have only P orbital, then the percentage of S character will be obviously 0%, right? If you have SP, then what will happen? 50%, 50%, right? 50% will be S character, 50% will be P character. If you have SP2, then 100% will be divided into 3. That means that S character will be 33%. Now what if you have SP3? SP3, that means there are 4 orbitals here, so that means that it will be 25%. Getting it? Yes? All right. So basically, here is something else also that you have to understand, and that is that more the S character, okay, more the S character percent, the bond length is less. And more S character means more electronegative. So let's just write it down, okay? Let me just write that down here. This is a trick that you can always use. What did I say? I said that more S character percentage. Yes, what did I say? Bond length is less. All right, yes. And the second point that I said is, more S character means more electronegativity, okay? If there is more S character, that means that more electronegative it is. Okay, all right guys, get it? Understood? Chalo, moving on, let's do a question here. What do you say? Let's do a question here. The question is the hybridization and the geometry of BrF3 molecules are. Okay, BrF3, bromine it is, yes, bromine and F3, correct? Okay. So let's take a look at it. Br, yes, Br, bromine and fluorine, both of them are in the chlorine, bromine, chlorine, bromine, right? So that means there are 7 electrons. So 1, 2, yes, 1, 2. Then it will be 3, 4, 5, right? 5, no, it has to be 7. So 1, 2, 3, 4, 5, 6, and 7, right? Yes. So instead of drawing it like this, if there are 7 electrons, that means that, okay, 7 electrons, right? So that means that there'll be 1 here, 1 lone pair here, then F, and then F. So 1, 2, 3, 4, 5, 6, 7, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Done? Everything clear? So that means that what will it be? It will be sp3d will also be present, right? sp3d and T-shaped. Option A is the correct answer. Make sense? Make sense, right? Absolutely correct. You guys got it. You guys got it. Yes. Okay. Now, moving on from here, let's do another question. The incorrect geometry is represented by incorrect geometry, my dear students. So that means that N. Let's do it for the first one. N is N has 5 electrons, right? 5 electrons. So 1, 2 here. Yes, 1 lone pair, and then it will be F. Is this trigonal planar? No, right? It's not trigonal planar, correct? So option A is our correct answer. Option A is our correct answer. It is not. It is trigonal pyramidal, everybody. If I stop this, then this looks like a pyramid, isn't it? So it will be trigonal pyramidal and sp3 hybridization. Gotcha, everybody? Great and amazing. So this is where we stop with VSEPR theory and hybridization. Now, where do we go? We go to valence bond theory. Okay, so what is valence bond theory? Valence bond theory is basically, valence bond theory, you also get to learn about it in coordination compounds, but here valence bond theory is basically, you have to understand this, that a metal, right? A metal, what do they do is, they will first empty their d orbital, then they will give it to those who are incoming and who wants to fill their electrons, right? They will first empty it, then they will hybridize it, and then they will give it to the other ones to fill it. This is VBT. 3 things I said. First, empty the d orbital, hybridize it, and then give it for filling. Like, hey, come fill it. That's it. Now in valence bond theory, let's read this and let's understand. To form a covalent bond, overlapping occurs between half-filled valence shell orbitals of the 2 atoms. What is happening? Overlapping occurs between half-filled valence shell orbitals of the two atoms. Okay. Resulting bond acquires a pair of electrons with opposite spin. You know that. Remember structure of atom we got to know that in an orbital, no two electrons can have all the quantum numbers to be same, right? Spin has to be opposite. So opposite spin makes sense. Yes. Resulting bond will acquire a pair of electrons with opposite spins to get stability. It cannot have the same spin anyway, right? Now the orbitals, they come closer to each other from the direction in which they think that there will be maximum overlapping. They want maximum overlapping, right? Maximum overlapping is a necessity here. So now that means we are saying that the covalent bond has directional character. What did we say? We said that covalent bond has directional character. That means covalent bond has direction, all right? And the extent of overlapping, the more amount of overlapping happens, more is the strength of the chemical bond. Obviously, if I'm not touching like this, if only this much is happening, that means you can easily break it. If the overlapping happens like this, now can you break it? You will have to push the other one, slide it off, and only then you will be able to break it off, right? Yes. So you get it? What is it? What does it say? It's saying 5 things, okay? 5 things. Basically, what? To form a covalent bond, overlapping happens between what? Half-filled valence shell orbital of the two atoms. Second, it's saying is second point is resulting bond acquires a pair of electrons with opposite spins. Okay, whatever bond you have created, the electrons will be of opposite spins. You know that in a bond, whenever I make a bond, let's say C and there is O, so this will be like this and this will be like this. There will be two opposite spins. Okay, get it? Second point. Third one is orbitals, they come closer from that direction in which they think maximum overlapping will happen. They want maximum overlapping. They can come like this, they can come like this, they can come like this, but maximum overlapping is necessary. Fourth one, they say covalent bond is directional. Great, obviously. It's coming from different direction. And the fifth point is more is the overlapping, more is the chemical bond strength. We got it? Yes? Great. Amazing then. Amazing. Now moving on. Okay. Extent of overlapping depends on two factors. Okay. One is nature of orbital. Nature of orbital. So you understand that S orbital is just a sphere, right? So what direction are we talking about? It's just a sphere, non-directional. Okay. Because it is non-directional, if there is S orbital involved, there is always less overlapping. But for P, D and F, you know how the P, D and F look like? Yes, P looks like a dumbbell, D looks like double dumbbell, F is even more complicated. So in these cases, there is more overlapping. P, D and F has more overlapping. S is just a sphere, it's non-directional, less overlapping. Gotcha? Great. Next one is nature of orbital. Nature of overlapping. So nature of orbital, we understood P, D and F has more overlapping, S has less overlapping. Nature of overlapping. Now see, if it is, you know how the Earth, guys, the Earth looks like this, right? This is your equatorial and this is your axis, correct? This is your axis, correct? This is your axis, right? So if it is coaxial, if this is your axis, now let's say there is another one who is coming like here only. If it is coaxial, then the overlapping is more. Okay, then the overlapping is more. If it is collateral, like say this is the one and there is another one, then the extent of overlapping is less. Okay, extent of overlapping is less. Now, if it is P and P, then the overlapping extent is more. If it is P and S, it is a little less. If it is S and S, it's even more less. Okay, all right, if it's even more less. Now, there are 3 different types of overlapping. There is positive overlapping, there is negative overlapping, and there is zero overlapping. When two atoms, when they come close to each other, there is an overlapping of atomic orbitals, right? But the atomic orbital overlapping can be of 3 types. It can be positive overlap, it can be negative overlap, it can be zero. Zero means no overlap, obviously. Zero means nothing, no overlapping has happened at all, okay? So what is positive overlap, what is negative overlap? Let's understand, okay? So, if I make this p orbital, okay, see this is my z-axis, guys, this is my z-axis here, this is my z-axis. On this axis, I have drawn a p orbital, I've made a p orbital. So what will I call it? I will call it pz. Make sense, nonsense? Makes sense, right? This is my z orbital, I've made pz, hai na? Okay, so pz. Now from here, s is coming. Now check it out, Positive, positive. Same phase, positive phase, same phase, everybody. Yes, same phase, everyone. If it is a same phase, okay, if the interaction is happening between same phase, then we call it a positive or in phase overlapping. Now check it out. This is again z-axis. There is a pz here. There is a pz from here. This side. Okay, what is happening? Positive, positive. Again, so it is a positive phase. Now, whenever there is a positive overlapping, the bond is formed that time. Whenever there is a positive overlapping, see, it is written bond is formed. Bond is formed during positive overlapping. Now, see, it can also form. This is what? This is not coaxial. Okay, this is not coaxial. This is what? Collateral. Collateral, like this. This is a P, this is a P. They are coming together. Here, see, the overlapping is less, right? But here, what can happen? It can go like this. Yes, overlapping is more. Here, what is happening? Overlapping is less. But positive, positive. If it like this, then see, bond is not forming. If it is like this, bond can form. It can also be like this. Py. This is your px on z-axis. What will happen? This is your x-axis, right? And this is your y-axis, correct? So see, this is your x-axis. This is your y-axis. These two are px. Here, collateral overlapping has happened. Bond has formed. Here, see, this is your z-axis. I just drew it and told you that this is your y-axis. See, py. Here also bond has formed. Now understand negative. Okay, see, a negative and a positive, pz and s here. What is happening? Bond is not formed. Positive and negative, once again, pz, both are pz, but they are out of phase. They are out phase. Here, what is happening? They are interacting, but it's opposite. The orbital is only opposite. So here, no bond is formed. Here, see, I just showed you, this, like this. If it is happening like this, here, no bond can form. No bond can form. It's opposite, okay? No bond can form. Here also, plus minus, out phase, no bond is formed. And it can also be zero overlapping. For example, see, here, this, but at this place, right at this curve, right at this node, to find an electron is what? Do you remember? Nodes. At this place, you are rarely going to find an electron. So even if there is even if it is coming like this, zero, no overlapping, okay? When the orientation of two interacting orbital is such that there is no overlapping of the orbital, we call it zero overlapping. Even it doesn't matter if they are out phase or in phase. It doesn't matter if it is positive or negative, but that means that zero overlapping. See, this is your px and this is your py, no overlapping. They're coming, they're already from, they're absolutely in two directions. This is your X, this is your Y. How will they overlap? Can they overlap? There is no overlapping. No overlapping. See, getting my point? Okay, all right. Now we come to something called as type of overlap and bond. So covalent bond forms, right? Covalent bond forms. When a covalent bond forms, you just saw that coaxial and collateral, right? Either it can be like this or it can be like this. So that means when it is head-on collision like this, when two heads are coming together, okay, it's called as a sigma bond. For example, if a S and an S like this, it comes like this, it's a sigma bond. If it is a P like this and a P like this, okay, plus and plus, this is what? This is also a sigma bond, okay? But if it is like this and like this, then this is your pi bond, okay? This is your pi bond. When a lateral, sideway or a parallel overlap happens, it's called as a pi bond. I am going to erase all of this because it looks very dirty, but I hope you get it, right? Yes, so in a covalent bond, whenever there are two bonds, there is a sigma bond and there is a pi bond. A sigma bond is because of head-on collision, and because of lateral, you call it to be a pi bond, okay? Let's read about the sigma bond and pi bond a little more, okay? So sigma bond, it is formed by end-to-end overlap, head-on collision of bonding orbitals along the internuclear axis. For example, let me show you this. Along the axis, this is a head-on collision, so this is going to be a sigma bond, okay? This is going to be a sigma bond. It is also called as axial overlap because it's happening on the axis, or it is just called as head overlap, okay? Or it's just called as head overlap, got it? Now we come to pi bond. This type of covalent bond is formed by the sidewise or lateral overlapping. See how these are? They are perpendicular to the internuclear axis. That means my axis is this. I have still taken, let's say, what happened? I have still taken the z-axis. This is my z-axis, but I have taken a px and a px, and these two, when they're overlapping, what is happening is my electron will be here, right? Right here will be my electron. So can I just draw it like this? This is where I'm going to find my electron cloud, right? Overlapping is happening. So these are the places where I'll find my electron. So that means I can just draw it like two plates. Yes, I can just draw it like two plates. So it looks like if this is my axis, these are the two places, these are the two spaces where I can find the charged clouds. And that is your pi bond, okay? That is your pi bond. Are you getting my point? Now in exam, you get something called as number of p pi bonds and number of p pi d pi bonds, okay? So when there is a p pi bond and when there is a p pi d pi bond, that you might have to find out, okay? That comes in the exam, especially in your JEE Mains and JEE Advanced, it does come. So understand this. How will you find out? Number one point is if there is a double bond between the second period element. Second period element, you know, what are the second period element? Second period element is your lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. These are all second period. First period is hydrogen and helium, okay? Hydrogen and helium don't even have the p orbital, they only have s orbital. But these, second period, they have only p orbitals, right? They don't have d. So it is going to be p pi. Whenever they are involved in bond making, close your eyes and write down p pi. If it is nitrogen, oxygen, boron, oxygen, carbon, nitrogen, carbon, oxygen, always p pi. They don't even have d orbitals. How will they participate to d pi, right? It will always be p pi. But if there is a third period element present, after oxygen, what do you have? Sulfur. After carbon, you have silicon. After nitrogen, you have phosphorus, right? Yes. So what do you do? Whenever these elements are present, it can either be p pi d pi or it can be p pi p pi. Okay. H3PO3. What? Let's take the example of H3PO3. Okay. H3PO3. If we take, that means that P is my central atom. It will be OH here, OH here, OH here, and then double bond O, PO3. PO3. Sorry. One mistake. It will be like this. Here will be H and here it will be O. Okay. Now what is the valency of phosphorus? Phosphorus has 5 electrons in the last shell. No doubt about it. Last shell, 5 electrons. But it cannot be 5 electrons. No. 8 minus 5, 3 electrons. So 3 bonds, we will consider it to be covalent. Okay. Let's consider these 3 bonds to be covalent. Here. This is our covalent bond. This is our covalent bond. And this also is a covalent bond. Okay. But now what am I going to do? I'm going to change that to be coordinate bond. See, this one I'm going to change it into a coordinate bond. Take a look at it. Yes. So now number of p pi d pi is equal to 1. Understood? Understood? Yes. Okay. So basically what you have to do is, what is the valency? This is the trick, my dear student. Remember it. Trick. Valency. What is the valency? If 2, then leave 2 bonds as it is. Rest you convert it into coordinate bond. If it is 3 valency, keep them as covalent bond. Whatever is remaining, convert it into coordinate bond. So that's the way you can find it out. Now you can take a homework and do it on yourself. Take the example of SO3 and do it as a homework. Okay, SO3. Do it for SO3 and find out how many p pi bonds are there and how many p pi d pi bonds are there. All right. Yes, do it on your own. Now, what are the combination of orbitals? How can orbitals combine? Orbitals can combine as S overlapping, SP overlapping, or it can be PP overlapping or PP overlapping like this also, right? Yes. So let's check out the SS overlapping. See what is happening here. S plus S orbitals, right? Yes, how they are overlapping like this, no direction. And the easiest example is H. They only have S orbitals, right? So obviously it is going to be SS overlap. Now see, for S and P orbital, S and P can combine like this or they can combine like this also, okay? Alright, S plus P, they can combine like this, and here is the example is HF. HF has a SP overlap, okay? It has a SP overlap. Now PP orbital can have, see, P and P orbital, they can combine like this, PP overlap, and the example is FF, okay? It can be FF or CL. Chlorine can also be like this, F and F can also be like this, alright? So this ends our VBT. Now we go to molecular orbital theory, which was given by Hund and Mulliken. You remember that Hund's rule? Yes, Hund's rule. And then there was a Mulliken scale and all, Pauling scale and all of that. So by that Mulliken, exactly. So it was given by Hund and Mulliken. What is MOT? MOT is molecular orbital theory. So they said that if there are 2 atomic orbitals, if they came nearer, 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 and if they overlap with each other, there will be two molecular orbitals. There won't be one molecular orbital, there will be two molecular orbitals. Two atomic orbitals are coming in, they will give rise to two molecular orbitals. Getting my point? Two atomic orbitals are coming, they are giving rise to two molecular orbitals, two atoms, two molecules, okay? Alright, now what is the molecule that you are getting? The combination of two atomic orbital will give you two molecular orbital. It will be basically, one of them will be anti-bonding molecular orbital and one of them will be bonding molecular orbital. Now the anti-bonding molecular orbital has higher energy than the bonding molecular orbital. So just like how atomic orbitals, just like how you fill the atomic orbitals, right? The filling of electrons in molecular orbital, it is exactly the same as, Auber principle, Hund's rule and Pauli's exclusion, right? How you fill the lower energy first, then you go to the higher energy. You always have to have, two electrons and then only you can do the pairing up, right? Exactly the same. Those things are followed here also, okay? Just like the structure of atom. But like I said, the energy of the bonding molecular orbital is lesser than energy of anti-bonding molecular orbital. Great. Okay. Now see, combination of atomic orbital, it has to be of comparable energy. You can't mix 1s and 2s and 1s and 2p together. No, it has to be 1s, 1s. It cannot be 1s and 2s. This is wrong. 1s will only combine and they form a 1s bonding molecular orbital and 1s anti-bonding molecular orbital. Getting my point? Yes, I'll show you, don't worry. So combining the atomic orbital, it has to overlap in a large extent. Greater the overlap, more stable will be the molecule formed. Okay. If the overlapping is less, it's not going to happen. Now, combining the atomic orbital, it must have the same symmetry. You can't keep one like this and one like this. No, that doesn't happen. Okay. If it is Z, then both of them has to be PZ and PZ. It cannot be PX and PY, PZ and PX. No. It has to be same. Okay. Then combination by addition. They are saying constructive interference. Have you seen that? Let's say that one of the C waves are coming, right? One of the C waves are coming. Then there is another one also coming. Both of them, they have combined. Now you see a big wave coming, right? A big wave is coming. Now imagine that one of the wave is coming and this other wave is going. Now what happened? Now these two, they combine and it has reduced the size of the wave, right? So this is your constructive interference. I think you studied this in physics also, and this is called as destructive interference, right? I think either you have studied or you are going to study. So when the two electron waves are in phase, that is positive and positive, right? They will give rise to the same sign, but it is going to be of a bigger wave function. That we are going to call it as psi b. Okay, let's call that to be psi b, because this is our linear combination of atomic orbitals. We are going to do LCAO. Okay. So psi b is basically, if this is your psi a and this is your psi capital B, we are going to call it psi b. Addition of wave function has happened. Very simple, very easy, right? Yes, very simple, very easy. It shows a higher amplitude than those two. Okay, higher amplitude than those two. So wave function for bonding molecular orbital is psi a plus psi b. Okay, psi b is the wave function of atom B and this psi a is the wave function of atom A. Okay, now combination of by subtraction, destructive interference. Remember what I told you? One of the C waves is coming and the other one is going. So what will happen? This one wants to come here, this one is pushing it away. So what happens? The wave becomes smaller. Okay, the wave becomes smaller. Now imagine if it is out of phase. One is positive, one is negative. So together what will happen is they will reduce the amplitude further. The wave will be reduced. The size of the wave, the amplitude of the wave, the maximum distance of the wave will be reduced here. It shows much less amplitude. So here, let's call this to be psi a. Okay, psi, small letter a. That means it will be psi a minus psi b. Okay, this is out of the phase. Okay, out of the phase. So now what we are saying is, if it is sigma, if it is just sigma, no star, just sigma is addition. If it is sigma star, that means it is subtraction. This means if it is sigma, this means that it is constructive interference. Okay, and this means that it is destructive interference. This is your destructive interference. This constructive one is your BMO, that is bonding molecular orbital. The destructive one is ABMO, that is anti-bonding molecular orbital. All right. What are we studying? We are still studying linear combination of atomic orbital. So this is what molecular orbital is telling us, and this is one of the best. Okay, this is one of the best. Now, how are you going to draw your atoms? Check it out. How are you going to draw this? Okay. Imagine that we have N2, nitrogen 2, right? Two nitrogen atoms are here. So that means that this is my nitrogen 1 and this is my nitrogen 1. Okay. Now what will happen is from this nitrogen, let's consider this to be your 1s orbital. So what will I do? I will have one orbital here, one here. Then I will do add one here, add one here. It has 14, right? N has 17, N has 17. Sorry. 7 electrons in the outermost shell of one nitrogen, 7 electrons in the outermost shell of the other nitrogen. So 7 plus 7, 14. Yes, I have only drawn 4 here. Only I have drawn 4 here. I have 10 more to draw. Okay, that I will show you. But you get the point, right? You get the point? Yes. Okay. Now moving on, what will happen is if there are two 1s atomic orbitals that are combining to form two molecular orbitals, then what will happen? The bonding molecular orbital sigma 1s and there will be anti-bonding sigma 1s. This will have a star. You will always put a star for the anti-bonding one. Okay. If it is 2s and 2p, then see what happens. If it is 2s and 2p, for 2s, you will again write sigma 2s and see sigma star 2s. That is it. 2s is done. But if it is 2p, now you will have 3 orbitals. Three orbitals, my dear student. You will have sigma 2pz, then you will have pi 2px and pi 2py. You will have sigma star 2pz and you will have the same pi star 2px and pi star 2py. Are you getting my point? Z is where they combine coaxially. But x and y are collateral. Do you remember? Z was this axis, this was your x, and this was your y, correct? So exactly, these two will be pi and z is sigma. Now let's draw it, everybody. Okay, now let's draw it. So if it is less than or equal to 14 electrons, let's take the example of nitrogen. Let's take the example of nitrogen N2. So see, in your exam, you don't have to decorate it like this. In your exam, how you can do it is, it's less than 14, right? So you write sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, okay? Then you have sigma 2pz, okay? Now what you're going to check it out, okay? Okay, now we are not going to draw sigma 2pz first. So this is where you differ, okay? This is what you have to remember. Till here, it's the same, everybody. Whatever I have written here, you're going to exactly copy it here also for more than. Let's say that this is oxygen. Oxygen has what? 6 plus 6, right? Oxygen has 6 plus 6. That means what? Sorry, am I saying it right? Yeah. No. 8 plus 8, 16, right? So 16 electrons here. So let's consider this to be O2. Now see what will happen here, okay? Same, 1s, sigma 1s, sigma star 1s, okay? Sigma 2s. You are again going to write sigma star 2s, okay? Now what changes? Check it out. What changes is here you are going to write 2. That is your pi 2px pi 2py. Here you are going to write sigma star 2pz, okay? Then you are going to write again 2 here. That is your pi star 2px and pi star 2py. And then finally here you are going to write sigma 2pz. This is going to be star and this will be not star. This is how you're going to draw it. Now in this case, what will change? In this case, it will be, check it out, you will draw here first. This will be your sigma 2pz. Then you're going to do like this. It will be pi 2px, pi 2py. Then again here, sigma star 2pz. Okay, and then it will be here again, pi star 2px, pi star 2py. So basically, this part is same, this part changes. Here you have to remember 2, 1, 2, 1. Here you have to remember 1, 2, 1, 2. Actually, no, I'm so sorry. Wait. It has to be 1, 2, 2, 1. 1, 2, and then here, okay? You have to remember 1, 2, 2, 1. Okay, this is what you have to remember. Now, N2, that means 14 electrons, right? 14 electrons. So let's fill it. 1, 2, 3, 4, 5, 6, okay? 7, 8, 9, 10, 11, 12, 13, 14. 14 electrons filled. Okay. Now see, here we have to fill oxygen, that is 16 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 and 16. Done? Getting my point? Now do you know that from here you can calculate bond order? From this you can calculate bond order. How do you calculate bond order? Bond order is basically equal to, let's write it with a different color here so that you can remember it. Bond order is basically equal to number of bonding molecular orbital electrons, BMO electrons, minus number of ABMO electrons divided by 2. That's it. You want to find the bond order? Let's check it out. See here. 1, 2, 3, 4, 5, 6, 7, 8. Yes. So that means bond order for nitrogen. Bond order of nitrogen. Okay. Let's check it out. See. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the bonding. And then here you have 1, 2, 3, 4, 5, 6. 6? No. Made a mistake. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. 10 electrons in the bonding. 10 electrons in the bonding. And here see. 1, 2, 3, 4. 4. 10 minus 4 divided by 2 is equal to 3. Now nitrogen has 3 bonds, isn't it? Nitrogen has 3 bonds, isn't it? Check it out. See, you calculated it. Now see how will you find out for oxygen? Okay, bond order for oxygen. Bond order of oxygen. See, figure it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in bonding, okay? And then in the anti-bonding you have 1, 2, 3, 4, 5 and 6. 6 divided by 2, 4 by 2 is 2. Oxygen is bonded by 2 double bond. There is a double bond, right? There is a double bond, right? Easy peasy, biryani tasty. So if the bond order is 0, it means that the molecule does not exist. It means that the species does not exist. If the bond order is 1, 2 and 3, it means that it is single bond, double bond and triple bond respectively. Now, it also tells you about magnetic property, my dear student. Check it out. There are 2 unpaired electrons here, right? There are 2 unpaired electrons here and here. That means that O2 is what? O2 is paramagnetic. If there are 1 or more electrons in the molecular orbitals are unpaired, you call it paramagnetic. But check it out here, everything is paired. If it is paired, that means it is diamagnetic. N2 is diamagnetic, O2 is paramagnetic. Now bond order is more, stability of molecule is more, but bond length is less. So nitrogen has a lesser bond length, oxygen has a little more bond length. Okay, all right, understanding everybody? Got it? Very clear? Absolutely. We are almost about to end the chapter, guys. We're almost about to end the chapter. I think another 8 to 9 slides and that's it. We're done. Now the common features among the species Cn minus, CO and NO plus R. Any idea? Cn minus, CO and NO plus R. Any idea, guys? Think about it. Think about it. Carbon has how many electrons in it? What is the atomic number of carbon? You know it. 4. What is the nitrogen? Nitrogen is 7. So 6 plus 7. How many electrons are there? How many electrons are there? Figure it out. Figure it out. Come on, quick. 6 plus 6 is 12. This is 13. But it says that it is minus. That means there are 14. That means there are 14. Yes. So bond order is going to be 3. We just calculated for 14 electron. It is 3, right? Yes. Now see, C and O. Carbon is 6. Oxygen is 8. 6 plus 8. How much? 8 plus 6 is again what? 14. 14. That means bond order is 3 again. NO plus nitrogen is 7. Oxygen is 8. How much is it going to be? 8 plus 7 is again 14, guys. Right? 8. No. O plus. So that means it is less. So 7 plus 7 is 14. Again, bond order is 3. And these are isoelectronic. Make sense or nonsense? Easy peasy biryani tasty. See, if these kind of things can come in exam, and they do, I will take care of some of the problems also, and you will see that these kind of questions do come in the exam, and it will be super easy and super simple for you. Okay? All right. All the 3 of them have 14 electrons. They're isoelectronic, and the bond order is 3. Correct? Next, which of the following is true? Tell me. Bond order is directly proportional to 1 by bond length. Directly proportional to bond energy. Is it? Bond order is inversely proportional to bond length. Yeah, bond order increases, bond length decreases. Bond length decreases and bond order increases. More is the number of bond, more is the energy. Option A totally makes sense. Right? We just did it. We just did it, everybody. Yeah, this is the correct. Okay. Now, of the species NO, NO plus, NO2 plus, and NO minus, the one with the minimum bond strength is one with the minimum bond strength. Okay, let's do it. N and O. So nitrogen has 7 electrons, oxygen has 8 electrons. So 8 plus 7 is 15 electrons, right? 15. Okay. So if it is more than 15, then how do we draw? If it is more than 15, so let's just draw it. No? Let's just draw it. So you will have 1s, sigma 1 star 1s, sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, right? Yes. Okay. Now what we're going to do is let's just draw it as this. Okay. This is NO. This is NO, right? NO is greater than 14. So that means that 1, 2, 2, 1. So it will be, sorry, sigma 2pz. It will be sigma 2pz. Here it will be pi 2px, pi 2py. Yes, then again 2. So pi star 2px, pi star 2py, and then finally 1, that is sigma. This is sigma star 2pz. Okay. All right. So let's do it for NO. N has 7 electrons. Oxygen has 8 electrons, right? So 7 plus 8 is 15. Yes. So let's do it. 15 means 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 here. Okay. 15 here. So that means what is the bond order, guys? What is the bond order? Check it out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 minus 1, 2, 3, 4, 5. 10 minus 5 divided by 2. That is 2.5. This is 2.5. Then we have NO plus. If it is NO plus, that means 1 electron gone. If it is 1 electron gone, that means 70. It means 14. So for NO plus, the bond order is for 14 electrons. How much is it? 14 electron bond order is 3, right? If it is NO2 plus, then how many will be there? Check it out. Let's do it here. Okay. NO2 plus, right? That means these 2 electrons will go. These 2 electrons will go. Correct? Yes. If these 2 electrons goes, then what will it be? 1, 2, 3, 4, 5, 6, 7, 8. Correct. So it will be 8 minus 1, 2, 3, 4. 8 minus 4 divided by 2 is equal to what? 2. Yes. 2. Correct. So NO2 plus bond order is 2. And then NO minus, that means there is another 1 electron. So we will add it here. NO minus another 1 electron. That means that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bond order is 10 minus 1, 2, 3, 4, 5, 6. 10 minus 6 is this divided by 2. So this will be 2. NO minus. Correct only, no? Correct only, right? The correct answer they say is minimum bond strength. Minimum bond strength. 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 here. Okay. 1, 2, 3, 4, 5, 6. 10 minus 6, 4 divided by 2 is equal to 2. Okay. All right. So the correct answer they are saying is, have I made a mistake here? For NO plus is also 3. NO plus is 3. NO2 plus is 2.5. Have I made a mistake, guys? NO2 plus they are saying it's 2.5. NO2 plus. NO2 plus. So 2 electrons will go, right? I don't think I've made a mistake, but they're saying that I've made a mistake. Okay. NO plus is 3, right? 2 electrons are gone. That means that what will be 2 electrons? You know what? Check it out once again. I think I might have made a mistake here just in case of NO2 plus. Just in case of NO2 plus, just calculate this once more. Or let's do it once again. 1, 2, 3, 4. Less than 14 electrons, right? Less than 14 electrons. So it will be this, 2, 1, 2, 1, right? So it will be this is star, these 2. And then this is star and this is star, correct? NO2 plus. Now NO has 7 electrons, O2 plus, that means 6. So 7 plus 6 is equal to 13 electrons, right? Yes, 13 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 and 13. So that means that bond order is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 minus 1, 2, 3, 4. 9 minus 4 divided by 2 is equal to 5 by 2. This is also 2.5. Correct. Yes, so I did make a mistake. The correct answer is NO minus. Now I have sorted it out. And with this note, everybody, we are done with the session here. Yes, I hope that you have understood everything. We will be doing more questions about this and let's use our concepts. Yes, stay tuned to this channel. I'll see you very soon with mole concept and stoichiometry for class 11 and I'll see you very soon with solid state for